Good day, this is MTH 101, General Mathematics 1. I will be taking you through study section 5, Solutions of Systems of Linear Equations. Learning outcome for this study section: after you have studied this section, you should be able to state the Cramer's rule. You should be able to solve systems of linear equations using Cramer's rule. You should be able to compute the inverse of a matrix, and finally you should be able to solve systems of linear equations using inverse method. Cramer's rule uses determinants. We make use of determinants to obtain the unknowns for a system of linear equations. What are we talking about? It means that if you want to make use of Cramer's rule to solve a system of linear equations, you make use of the determinants, and we are going to see how we are going to solve some of these problems using this same rule. And if you want to use Cramer's rule, there are some steps that you have to follow. The first is you have to compute the original determinant of the coefficient matrix, as you will see later on. Secondly, you have to replace the column in the coefficient matrix with the column of vector b on the right side. As you can see on the slide, the vector b is towards your right side, which is b1, b2, b3 in a matrix form. Also, you have to replace the column vector b by the second column in the coefficient matrix, and you then compute the second determinant. What are we saying? You will be replacing the vector, the original matrix. You will be replacing the column by vector b1, b2, b3, and you do that consecutively. Also, you repeat the process until all the columns of the coefficient matrix have been replaced, and after that, you use a simple formula, which is your x1 is equal to your first determinant over the original determinant of the matrix. For your x1, use that for your x2, x3 to obtain the unknowns, as you can see from this slide. Now let us see how we are going to obtain the determinant for our original coefficient matrix. Let's see how we are going to go about that. Now, given this as your original matrix, let's see how we are going to go about it in finding our determinant. Now, I want you to note that your sign, if you want to find your determinant, will be plus for the first column, minus for the second column, and plus for the third column. Now, if you want to obtain your matrix, your determinant for this matrix A, what you need to do is to take your first element, which is A11, and from that element down, you cross it down the line, and the corresponding row towards your right side, you cross it. Now, how you are going to come about this is to bring out that element, which is plus A11. Don't forget the sign, and you put a sign to show that you are calculating the determinant. Then you take these four elements, which are not part of the ones that you removed. A22, then A32, A23, and A33. Now you continue with A12. You do the same procedure, a similar procedure. From that element A12, you cross it down the line, and you cross it to obtain your determinant for that. Do not forget the sign that it's going to be A12, and you are going to be left with A21, A31, A23, and A33. A21, A23, A33, A31, A31, and A33. Now, for the last one, from your A13, I hope you are not going to mind the way I'm crossing it, just for you to have the understanding of what you are doing. You can see that we have eliminated these elements towards your right side and down. You are left with this element. So do not forget the sign, that you have positive up above, then A, that will give you A13, and then you are left with A21, A22, A31, A32. And from this you can obtain your determinant for A, matrix A. Now, this is the sign, or you can represent it with this sign. It's called like a delta sign. Then from this you can obtain your A, because A11. This will now be A22 multiplied by A33 minus your A32 multiplied by your A23. Do not forget the sign, minus A12 into bracket A21 A33 minus A31 A23. All you need to do is to do a cross multiplication while you are trying to obtain your determinant. And you do the same thing, a similar case for your A13. In that case, it will now be plus A13 into bracket A21 A32 minus A31 A22. I don't want you to make mistake. You know we are continuing from this place. This positive sign is from this place. So continue up to this place. Now from that, you'll be able to obtain, after factorizing, after obtaining your, solving all this multiplication, you'll be able to obtain your determinant for matrix A. Now remember that we have obtained our determinant for this original coefficient, matrix A, which is our delta. Now, if we are now going to obtain three others determinants, which are like a sub-determinant, by replacing this B1, B2, B3 into this original matrix in order to get other determinants that we use in our formula to obtain our unknowns. Now, what are we going to do? It means that you have another coordinate matrix by replacing the first column with your vector B, which is B1, B2, B3, and you have your A12, A13, A22, A23, then A32, A33. Following the same similar procedure from this place, you can obtain another determinant, which is going to give you your delta 1. And you follow the same procedure again by replacing by what you need to do is to replace this B1, B2, B3, you put it into the second column to give you another determinant. Now it means if you follow the same procedure, you obtain a value for this determinant. You can also find another one, A11, A12, A21, sorry, A31. Then you replace it. In this case, you give your second column, 2, 3, B3. then you have A13, A23, A33, and you obtain another determinant, which is your delta 2. You follow the same procedure to, you know, we after this one, we got another determinant. Don't make mistake. We follow this step after this one. Let's see, to obtain our third determinant, apart from the original determinant we obtained the other time. Alright, now you put a vector B towards the last column. You have A11, A21, A31, and A12, A22, A32, B1, B2, B3. To obtain that, if you do the determinant, you obtain your. Now let's see how we are now going to obtain our values for our x1, x2, x3 by making use of all these determinants that we have calculated. In order to calculate the unknown, you use this formula. To get x1, it means your x1 is equal to delta 1, which is your first determinant, over the original determinant that we've obtained from matrix A. Do not forget. To get your x2, x2 will be determinant of when we it was the B vector was in the second column over your original determinant of matrix A. And x3 is because of the determinant you obtained when your vector B was in the third column over the determinant of matrix A. So with this formula you can obtain your x1, x2, x3. If you are given a question to solve, all you need to do is to make use of the procedures that you have just done now to obtain your values. So let's go back to the slide. As you can see from the slide, we obtain our original determinant from matrix A, as you can see. Then we obtain other determinants, such as AX1 determinant. That was when we were trying to obtain value for the x1, determinant x1, determinant x2, and determinant x3. And we made use of the formula x1 is equal to delta 1 over delta, x2 is equal to that of the second one and the third one. So if you follow the same procedure, you'll be able to obtain their corresponding value. This is an example of a linear equation using Cramer's rule. We are asked to follow the system equation to obtain the unknowns, which are x, y, and z, using Cramer's rule. As you can see from the slide, we obtain our A, matrix A, to be 2 minus 3, 1, 1, 2, minus 4, minus 3, 5, and 5. And we have our unknown to be x, y, and z. While our B vector, we have 3, 6, and 8. And if you follow the same rule, we obtain our determinant for matrix A, which we got 50, and we replace the first column of the matrix A with vector B, which has 36, 8 in the first column, as you can see from matrix AX, to obtain our determinant for the first, the second determinant. And we follow the same procedure to obtain that of AY and AZ. And lastly, we make use of the formula to obtain our different values for x, y, and z respectively. So if you follow this simple calculation, you should be able to solve other problems regarding Cramer's rule. Let's go to solution of systems of linear equations using inverse method. This time we are not using Cramer's rule, but instead we are using inverse method. But like Cramer's rule, inverse method also has some procedures that you have to follow if you want to obtain your unknowns. The first one is to get your minor. The second is to get your cofactors. The third step is to get the matrix of the cofactors. And after that, you get your adjoint. After that, you determine the determinants, and you compute all the all what you've gotten. That is from your minors, cofactors, and so on and so forth, and you compute them using the formula in number 6, as you can see, VI. So let's see how we go about it in case we have a problem where we have to solve using this inverse method. Let's take, for example, this question. If you want to solve this question, how do you go about it using the inverse method? The first thing you have to do is to write it out in a matrix form. You write it out in a matrix form. If you do that, you will get the what you can see, the matrix form on the slide. The first represents your matrix A, while that X represents your unknowns. I don't want you to get confused with that X. You can see that it's indicated that it's in capital letter. So don't get confused with the first unknown, which is your X. So you have your X, Y, and Z, and you have your matrix B. Do not forget what I told you earlier on, that you have to follow some steps. The first step you have to follow is to determine your determinants for matrix A. And as we have done it the other time, you can get that easily by calculating it, computing it, and we got it to be 25. Now, after that, you find minor of matrix A. How do you go about this minor of matrix A? I will do it now so that you can see. Now, to obtain your minor for this matrix, what you need to do is to you take the first element. Now, that first element, you cancel out the column, the full column. That is the first column, and the corresponding row. Now, if you do that for this matrix now, as you can see, when you cross out B2, you are left with your -2, 1, 1, and -1. That is how to get the minor for an element. Now, to get the second one, that is the second element on your row 1, the first row, you pick 2, cancel out the first, the column where you have the first one, which is 2, towards the downward, and you cancel that one, the corresponding row again. So you have 3, 2, and 1, -1. 3, 2, and your 1 and -1. You repeat the same procedure for the last element in the first row, and if you do that, it means you are left with your 3 minus 2 and 1. 3 minus 2 and 2 and 1. 2 and 1. You follow the same procedure for the second row. Now, from this, now you can obtain, that is your minor for matrix A. Now, if you want to find your cofactor, all you need to do is just to add your sign, plus, negative, plus, negative, plus, negative, and plus. So it means that you are doing two things at the same time. You have obtained your minor for the matrix, and you have obtained your cofactor. Now, if you want to get a value for the first element, what you need to do is to multiply -2 multiplied by -1 minus 1. So let me do that so that you can have an understanding of what we are talking about. What you are going to do, what you are going to obtain is -2 times -1 minus 1 multiplied by 1. And through that you can obtain your value for the first element. And that is going to give you what? It's going to give you 2 minus 1, which is equal to 1. which means that your first element will be 1. You repeat the same procedure for the second element, third element, and so on and so forth to obtain the value. Let's see what it will look like after obtaining our different element for the values. You are going to have 1 for the first element, as we did now, 5 for the second element, 7 for the third element, 4 for the first element in the second row, -5 for the second element in the second row, that is the second element, and 3 for the last element in the second row, while you have different values for the third row. It means you have obtained your cofactor and your minor. Now let's continue. Now if you want to obtain the adjoint for this matrix, if you want to obtain the inverse matrix, it means that even from your cofactor you must obtain your adjoint. How do you do that? Now for your cofactor that we just obtained, we want to obtain our adjoint. How are you going to do that? All you need to do is to invert this element apart from your diagonal matrix, which is 1 - 5 - 8. It means you change this one, you bring it to the first row, while you take this, you bring it back to the first column, and you do that for this interchangeably. And after that, if you are able to do that, you will obtain, I told you, your diagonal matrix must not change. What you need to do is to change this. What you need to do is to, you bring, it means that your 4 and 6 will be here, while your 5 and 7 will be here, and this becomes 3, and this becomes, and through this, you have obtained your adjoints. Let's go back to our slide and continue. So that's our adjoints, as you can see on the slide. Now, do not forget that we said earlier on that if you want to obtain your inverse matrix, you use the formula, as you can see on the slide, that's your matrix A. So remember that we obtained our coefficient, our matrix for A, our determinant for matrix A the other time to be 50, to be 25, sorry. So when you replace that 25, you put it, you compute it, you substitute in your formula, you are going to obtain your A inverse to be equal to 1/25 into that adjoint, the matrix that we just got. And if you divide each element by 25, you obtain a value for your A inverse. And if you do that, and I want you to let me explain how we got our formula to calculate the A inverse. You know, the other time we said your A x is equal to B from your equations, from the equation from the beginning, AX is equal to B. Now, if you want to make X the subject of formula, which represent our unknowns, as I said earlier on, X represents unknown. It means that you divide both sides by A. And when you divide both sides by A, you have B over A. And from here you can obtain your X. It means that your X is equal to B over A. In other words, you can say your X is equal to A inverse. That's the reason why we have to obtain our A inverse. So that was how we obtained the formula for X. And as you can see, you can from your X now, replacing it by your A inverse and my B vector, the matrix was the B vector, which is 5 minuses and 1. You can calculate your X, your unknowns. You can obtain your unknowns. Now, do not forget that this X represents our unknowns, which are X, Y, and Z. And do not forget that this formula represents A inverse and this represents B. Now, how are we going to obtain our unknowns for which are X, Y, and Z? What you need to do is to multiply this inverse matrix by the B vector. and from that you can have something like 1/25 multiplied by 5 plus 4/25 multiplied by -6 plus 6/25 multiplied by -1. You are going to repeat the same step, the same procedure for the second row and the third row. Now, you repeat the same procedure for the second row and the third row to obtain what you can see on the slide. So, after solving it, you obtain 3 values for your unknown. X is equal to -1, 2, and 1. Therefore, it means that your X is equal to -1, your Y is equal to 2, and your Z is equal to 1. So through this method, inverse method, you can obtain your unknowns for a system equation. Thanks for listening.